Or in this case, because it was a simple example, we could actually calculate the exact fidelity and compare. And you see they are on top. So what do you get here? You get that initially you see the fidelity is 1. Stay 1 for a few layers, because initially we don't truncate anything. The MPS can actually catch that exactly for the given rank. So everything is exact. And when we increase the rank, so 10, 20, and 50 are very small. Huh? You can go to, if you are motivated, you can go to 1,000 typically. 2,000. You see that the green one continue to be 1 for a little bit longer than the red one, because we have a bigger bond dimension, so we we can absorb a bit more entanglement. And then at some point, you need to truncate. And these things decays exponentially. Oops. It decays exponentially, and the slope changes depending on the rank. So if you have a bigger rank, you can actually keep more things. So you actually decay in a slower way. So you do have a rate, like an error rate, as in a quantum computer, although the origin is completely different. For instance, here, you are not making any error when you are doing single qubit gate, while in a real quantum computer, you do errors when you do single qubit gate. In a real quantum computer, you are also doing errors when you do nothing because of decoherence. Here, you don't. Here, you're only making errors when you do a 2-qubit gate. So it's not you should not think that you should compare, could use this to understand what's going on in a quantum computer. No, you can't. Right? So, but what you can use this for is to say, look, at this level of fidelity, this is the resources I need to simulate on a classical computer for this circuit. And then you know that if you don't have this level of fidelity in your quantum computer, then you are no match for this simulator. It's a very important conclusion, because if you read just about anything in the public press about quantum computing, they always report on the number of qubits. And they should report first on what is the fidelity. But only figure that matters is the fidelity. Qubits, I mean, we find a way to scale up to more qubits. Okay. If you need millions, it's going to be probably not going to happen, but I would say it's much easier to do twice as many qubits than to increase the fidelity. The fidelity, you have to deal with physics. You need to do something. I mean, unless you start to do quantum error correction, that's very distant future. So whenever you see someone in the press reporting on number of qubits, you should really wonder, okay, yeah, but what happened to the fidelity? It's very difficult to scale up a system without losing in fidelity. So if you look at typical numbers that people will give you, they always give you the number for actually 2 qubits. They take 2 qubits, they do 2-qubit gates, a bunch of them, they extract the fidelity, and they give you the C0 is at 99%. When they are very honest, they also give you statistics about what's going on everywhere in the chip. Because you might get this one at 99% and this one at 98%. And if you actually look at a paper on quantum computing, like most of them, they have 100 qubit, but for a given experiment, they only use 20 because they don't have the fidelity to use more. On the 20, typically, they show you on the chip, so they use some sort of drawing, like they use this part of the chip or that part of the chip. And it's really dependent on the weather. Like on this day, these qubits are behaving better than those qubits, so they are using the ones that have the best fidelities. Okay, well, that just comment a bit on what we did at the beginning of the lecture. I lost. This is the same thing, but now the DMRG algorithm. You see, so if you have like a bunch of gates, here it's some sort of MPS, but where each tensor actually represents several qubits. And if I want to optimize, the one here in the middle, I should to start from that, add all the layers, and then I make a hole, as we discussed in the DMRG. And then I need to contract this guy, and you need to find the best order of contraction. And it's not totally trivial, but this is the best you can do. So I have a few snapshots and then at the end you get this ugly guy here. And this is the best thing you can put back here to optimize the thing. And then you can actually go through these three tensors one after the other and optimize. So this is something we actually did for the actual quantum supremacy experiment. And that's why we grouped qubits. We wanted to compress as little as possible, so it was really see how far we could go. Bottom line, we can reach the same fidelity that they had at that time on a workstation, but that was a bit on the limit of what we could do. So now the new experiment with 70 qubits, I didn't try, honestly. I get tired of this, but probably we can do. With the technique at the level of which we are, some other people took a different approach in China, like Pan and Zhang. And I think that if we combine both, we can probably still match what they have now. But at some point, it will be unmatchable. So there is no question about the fact of quantum supremacy in the sense that at some point, it becomes impossible to simulate. But I challenge the name supremacy, right? Because if I also take a glass and I throw it against the wall, predicting the shape of the small pieces that will come out is also impossible. And nobody discusses about classical supremacy or glass-breaking supremacy or anything of the sort. But in that sense, there are tons of problems that we don't know how to simulate in physics and in real life. It's become a bit pointless to epistemological statement. On one of these curves, I think the one on the down right, it's QAOA. So QAOA is one of the algorithms that actually has been put forward a lot for doing classical optimization with quantum computer. And it is much more structured than the random circuit. On this one, we immediately got a gain of 3 orders of magnitude in fidelity in these simulations, which means that even though it will be tough for 70 qubits to actually run a random circuit, they will need to go to much bigger system on much better fidelity than they have now to match what we can do on the actual quantum algorithm. Cost interpolation. So this is essentially a drawing I did on the blackboard, but now you see some actual data. So this is the error that you have. The matrix is actually given here. It's an explicit form. So it's you don't need to actually build the matrix. You just give this function that takes I and j and returns the cosine of this times cosine of the other plus a fraction. Okay, this one is particularly low rank. And you see, you take the first pivot, everything is yellow around here. Is yellow, so it's mean error of order 1, not very good. The biggest error is here, so you put your second pivot here. You immediately see that the entire row and column becomes deep blue, which means error 0, because by construction, the cross interpolation is exact on the pivot. It starts to be a bit greenish around here. And greenish already means 2 digits, so it's not so bad. You have the third pivot, you are getting to the 4th digit real. And after 6 pivot, essentially everything is done. Okay.
When you say error, you mean NRJ minus
yes.
A constant population.
Exactly. For each pixel, we just computed the difference between the approximation on the exact thing. You cannot necessarily do that. I mean, for TCI, you can do that on every pixel because you have an exponentially large number of them. What you do is, for instance, you can do. So first, you have the error that you have seen during the training on the pi matrix compared to the cross interpolation. So this we call the pivot error. In machine learning, it would be called a training error, because it's an error on the training sample, the dataset, like the dataset that you actually have used for building your approximation. but it's a very stringent one because it's a training error, but you are always looking for the worst error. You are not making your life easy. You're really like looking, okay, where is it that I'm doing badly? Okay, here. So this is my error that I report. I don't report everything below. But it's still a testing error, training error. Now, what you want to do is to also produce points that the algorithm has never seen and compare the approximation with thing. You can also do that. So for instance, we typically use Metropolis algorithm. We sample the function, absolute value of the function. You get a million sample. You calculate the million approximation. If for this million sample, you get 8 digits correctly with the approximation, you start to trust that your thing is correct. Sometimes you have other way to trust. For instance, if you know that your function is normalized to 1 because it's a wave function, you can calculate the norm of the one that you have trained. If you find 1, it's close to impossible to imagine that you you miss something. Yeah.
Can you go to something like machine precision there, like or approach it because you're in -4? So
now we get stuck at machine precision is a complex number. So a floating number is encoded double precision with 8 bytes, so 64 bits. I can't remember how many are used for the exponent and how many for the, but probably you do.
Well, like I don't know.
But you have essentially 15 digits. The best you can get is typically 15 digits. I think we never got better than 12, 12 or 13. So you lose a bit when you do all this multiplication of matrices. You lose probably 2 digits.
And how many pivots would you need for that?
Oh, that depends drastically on the problem.
Because here, if you would do the color scheme differently, like you would still see this horizontal and vertical lines, right?
Yes. Yes.
Even in the
those are exact. Like there is no. The rank really depends drastically on the problem. Yeah. In practice, we rarely go above a couple of hundred. Essentially, either it works very well, and with 100 you're already in business, or it doesn't, and then you have to push, but then you only do that when you are super motivated by the problem. You really want to solve this problem. If it is Hubbard model, I'm ready to go to 40,000. But at the moment we are, especially for this quantics game, it's very new. I mean, there is essentially 1 paper per equation for partial differential equation or something like that. And not all of them has been covered. So now we are more like looking for what's working right now. On the stuff that it doesn't work, we will study it later. So right now the rank are pretty small.
So if you have 1 paper per partial differential equation, can you already say what works and what does not work?
Yes. I will comment at the end if you want.
Okay.
There is one more. I mean, there is one difficulty still which has not been solved. And if we solve it, we just replace everything on the market. But it's a strong one. I will discuss this.
Okay.
This is something I like. Cross extrapolation. And this is something you can use. Actually, it has nothing to do with tensor networks. And it's a very general thing. Suppose that you have 2 variables in your problem. For instance, this would be like, I don't know, in our case, it was interaction and time. But it could be interaction and temperature or something like that. So it happens very often that you know how to calculate something, let's say for small interaction. Let's say for small interaction, I can calculate for all times. So I get all this data here. To a certain level of interaction, I know how to calculate. But also, for small times, or high temperature, for instance, could be, it's an easy problem for high temperature, so I can calculate for all interaction. So it happens very often that you have a problem like that. We have 2 parameters, 2 control parameters, and you can actually compute this corner. Right? But what you would like to do is to get things here, of course, when you have large time, large interaction, the difficult problem. So you may want to, you have to do some sort of extrapolation, right? So you might try to extrapolate this way, from small interaction to large interaction, or you might try to extrapolate that way for small times to large times. Not easy. Anyway, any kind of extrapolation relies on an assumption. Like it's not always explicit. Sometimes people don't really say anything about it, but you assume something. On one possible assumption is that this function of x and y is actually not too entangled. So it actually, as a matrix of x and y, it has a low rank. If it is the case, then you can use cross interpolation. You can use cross interpolation to calculate everywhere from the knowledge of this cross. So now it's the same thing as cross interpolation, except that you force the pivot to be in this corner. Right? So that you use the matrix A11, A21, and A12, you actually have them. And this would be the A22 matrix. Right? So if you have a problem like that, on this here you have an example for the same matrix as before. Now you see the pivots, they are all here. And it does not converge as fast as cross interpolation because instead of looking at the biggest error, you are just looking at the biggest error. I mean, the biggest, you can only put your pivots in the corner where you actually have the data. So it's not as good, but we have the theorem that if it is a low-rank matrix, then it should be exact. And so in practice, it works surprisingly very well. So we have a couple of calculations that we did with this. So here it's a toy example, but you see this is the data that you have. Like you have long time here, but for small value of y, and here for at short time you have a whole value of time, and it was able to actually reconstruct all the things here, even though it's not trivial, almost perfectly. Just mention it in case you have a problem like that. It's worth a try. And it's controllable. You can just increase the rank and see if it converges or not. You get an error bar. This is an example of an integral. So in this case, it's cosine. So it's in 10 dimensions. Cosine of 10 times the sum of the square of the variables times exponential minus then the sum of the variables to the power 4. Whatever. You give this function to TCI, and this is the error versus number of evaluation of the function, so number of times you actually call it. And you see it goes down to 8 digits, pretty much whatever. Convergence is something like 1 over number of evaluation to the power 4, which is pretty good. Remember that Monte Carlo is 1 over square root of n. So Monte Carlo means you add factor 100, you get 1 digit. Here you get factor 100, you get 8 more digits. Yes?
Is this function just an example?
Yes. Just an example.
Like
No, this is just, we put that at the beginning of the paper to just give something concrete people could think about, but you can replace it by anything you want. The convergence will depend on what you do, of the function. It might not be that fast, it might not converge, it might converge faster. Here we use this is not using quantics, it's using regular quadrature. So GK15 means Gauss-Conrad 15. So it's a regular Gaussian quadrature with 15 points per dimension. So that's a total of 15 points to the power 10. Here, 61 points to the power 10. Age of the universe, etc. You know it. And you see that, for instance, the orange one here, no, the blue one here, it's saturated here at 10 to the minus 4. This saturation means that you are actually controlled by the fact that you don't have enough points. So 15 to the power 10 point was not enough. So that's why it's saturated. So the factorization itself, TCI itself, is exact. It's better than this precision. If you go to 21 points, you get the same thing with better than 7 digits. And if you want to go beyond that, you need to have at least 41 points. And then, I mean, I didn't continue, but the curve continued. Yes?
So what do you use here as the benchmark? Because I assume this
No benchmark.
So
this we benchmark against ourselves. And this is actually the point of this particular integral. There is no other technique on the planet that can calculate this gap that I'm aware of. Why? Because it's 10D on 10D, and also because of the cosine. So the cosine actually oscillates like crazy. So Monte Carlo fails completely for this case. On the 10D, essentially, the only thing you have is Monte Carlo. Like a quadrature, regular quadrature, even advanced ones, they fail automatically. There is a bunch of techniques known as low discrepancy sequence. So Sobolev things, they fail too for the same reason. So for this particular integral, I have no benchmark. But it doesn't mean that we so okay, that's only we benchmarked for other integrals if we could calculate analytically. We always check that the values is the same as the one we can always call the function, so we can always test the approximation. I mean, you can do a bunch of things to convince yourself that everything is under control. But at the end of the day, if you have a single technique to calculate something, then you are essentially away from the border of the swimming pool. You have to, you have to swim. Yeah. So we compare to our own case, which was converged in chi and in number of points. And we had it, I think in the paper we put it, I think we have it with 12 digits. But I mean, we could also compare against something that you can calculate otherwise, but then it's like, okay, yes, but you can calculate it otherwise. This one, I don't know. And so if you want to try it, there is this website. You can actually try TCI. It's open source. It's in Julia, Python, and C++. That's an example of quantics. So for this particular function, that's in 2D. For rank 1, rank 5, rank 20, and rank 50. You see as you put more pivots, you see the function appearing. What is interesting in this example is that you see there is a bunch of cosine at different scales, which is a particularly good example for quantics, right? So in this case, I think we put 40 bits per dimension. So it's essentially, that means a trillion point per dimension. So that's so there are in total 10 to the 24 points. So it's totally out of any possibility, but far from anything that you could do with regular, I don't know, finite element or anything. And when you look at the final result, you can zoom here, and you can zoom on the zoom. And then here there is a very tiny square. If you zoom on it, you see this horizontal lines. They correspond to the last thing that oscillate like with 10 to the -7, like very last frequency. And so this is actually very low rank. So the total number of numbers that you need to fill the NPS, to fill all this, is here 10 to the 5, so 100,000 numbers. While the total number of pixels is 10 to the 24, so the compression level here is incredible. Of course, it's an example which has been made up for that. So, but just to say that there are at least some examples where you can address that with this kind of approximation, and there is no way you can do it in reality. So this one, now we start to slowly to go to real things. This is a hydrogen atom. The hydrogen atom, in this case, we actually know what are the orbitals of the hydrogen atoms. There are 3D orbitals. And here what we did was, so we took 1Z, 2PZ, and a 3D orbital and a 4F orbital. We gave them to TCI. We actually calculated the energy of this orbital. So we have in this case, we have an analytical formula. It's the Rydberg divided by n squared. But then you can also calculate it using MPO, MPS. So you have an MPO So actually, maybe I should write a couple of things here. So actually, my goal today is to try to. So I'm going to discuss partial differential equation for a bit more, and then I want to go back to the many-body problem to see what can actually all this bring to the problem, and then reintroduce the quantum computer and compare a bit also all these approaches with quantum computers. Yes, so hydrogen atom. So you have Laplacian psi plus e squared over 4 minus 4 pi r psi equal e psi on psi is a function of x, y, z. So in this case, we actually knew the answer. So we gave the answer to TCI. Laplacian, we just saw this morning that using the tensor network, you can construct the Laplacian. So using the magic tensor, you can construct the Laplacian. 1 over r. 1 over r, you just give it to TCI. Give it to TCI, it's going to give you an MPS, rank 30 or so, to get a good precision. And then you want to turn that into a diagonal matrix. And to do that, you just put the copy the copy operator. And that's now we have an MPO, which is diagonal, which corresponds to multiplying by 1 over r. And so I can apply this and this to my function, multiply by psi on the other side, and I get the energy, and I can compare that with the known result. And you see, and now can we go back to yeah? So we will be switching back and forth. I know it's terribly annoying. Yes. This is a kind of error that you get versus rank. And you see, you get at some point you get something like 6 digits. It's saturate. It's saturate because we use, I think, in this case, 20-bit per dimension, or maybe 15. I can't remember for this particular one. So let's say 20. Oh, we've been up to 20. So typically 20 means 1,000,000 points per dimension. So that's 10 to the 18 point in total. So again, once again, it's far beyond what we can do with traditional techniques. So we don't know how to actually do that with traditional techniques.
Why does it saturate sort of to a higher, to a lower precision for S wave than D wave? Okay,
that's a very stupid reason. Is that for the number of bits, the F orbital is much larger. And so actually, we should have on the box we chose the same box for all of them. We didn't bother to actually. So this is the box where you are doing the orbital. Let's say the F orbital is like this, and the S orbital is like that. So you actually have less points. It's a discretization which is not as good for the okay. But you can get to 8, 9 digits if you want. So you can control this accuracy. What you want is something better than 10 to minus 3. Why 10 to minus 3? Because this is in R3s. This is in R3, and 1 R3 is 27 electron volt. 1 electron volt is 10,000 Kelvin. And so 10 to the minus 3 correspond to room temperature, essentially. So in chemistry, you start to be happy when you can actually reach precision better than room temperature. Because if you don't know your energy plus or minus 300 K, then how are you going to decide whether this chemical reaction is allowed or not allowed? 10 to the -3 is actually the start to be okay. I mean, chemists are extremely happy when they get 10 to the -3, so 1 milliard. What we would really want is 10 to the -4. With the 10 to the -4, you still need to take into account spin orbit corrections, fluctuation of the actually due to the phonon of your the problem also itself has to be complexified a little bit. So which is one of the most I mean, main reason we stop at 10 to the -6 is because it's already much below what people are targeting. So in the previous case, we actually knew exactly what the orbital looked like. But there are, I mean, as soon as you complicate the problem a little bit, for instance, over the epsilon. So now you have 2 protons, 1 electron, so it's H2 plus. So it's still a Schrödinger equation. Still a Schrödinger equation, but a more complex one. Actually, you don't need to change. Okay. You don't even need to change the blackboard because the equation was already there. So now you can, so your TCI, I mean, you don't even need to TCI the Laplacian, we can construct it. This one you TCI, this one you TCI too. Now you want to find the ground state, and you don't know the ground state, so you need to calculate it. So you can do that using DMRG, right? It's a MPO, MPS eigenvalue problem. So you can really use DMRG. So a technique that has been designed to solve many problems, but in this case, you actually use it to solve your partial differential equation. And it works like a charm. Here you get some comparison with the best you can do with Gaussian orbitals, which is the standard technique in computational chemistry. And we actually get more digits, systematically more digits than them. On the method scale, I mean, you can really do more complex things like that.
Is this FCI or the Gaussian?
No, so you can't talk about FCI because it's a single electron problem. So so here you just compare with the basis set. So you see, for instance, typically the best you can afford is typically so this one is CCPV 5Z, so it's 5 zeta. So you don't want to enter into the realm of Gaussian orbitals, but it's a basis set that has been optimized a lot, that contains a lot of it's a big basis set, so actually you can use it for this problem because it's a small problem, but you wouldn't be able to use it for anything large. And we get, you see, if you look at the numbers here, for instance, it's okay for H2 plus, we get 1 more digit. Like here it's 14 microartery, and we are at the 1 microartery level, and it's using already 200 Gaussian, which is a mess. Oops. For helium H2 plus, helium H2 plus, then the error is even larger. And we are essentially, this is the reference calculation. We didn't know, we couldn't find anything. So we got at least 1 or 2 digits more than they could get. We consider that we have now the reference calculation.
Being a mess in terms of class. Difficult.
Yeah, also the thing about this Gaussian thing is that they have been essentially made by hand. So it's you essentially you make a Gaussian. So I will discuss a bit the Gaussian basis set a bit later, but you essentially you make a basis set which is bad. Then you put more Gaussians to make it a better one. You call it double zeta. You add more Gaussians, you make it better. You call it triple zeta. But each time you optimize it in a very in manual way, and then you try to extrapolate this from double zeta, triple zeta, quadruple zeta, 5 zeta to the thermodynamic limit. But the thing is that I mean, it's not like you are extrapolating something physical, you are extrapolating something that you designed. So it depends a lot on so there are as many extrapolations as there are basis sets, sometimes, most of the time, multiple extrapolation for the same basis set. I mean, these guys, they worked for 30 years, they did an amazing job, but it's really not a systematic method.
How about using the hydrogen orbitals? Doesn't work at all?
Extremely bad, extremely bad.
Okay.
Yeah. So what you want to do is typically okay, let me discuss that. Actually, can I say what is
Yeah, of course, the integrals are harder to make. Yeah.
maybe I will come back to that later. Let me
Sure,
keep the order
sure,
of the
sure,
slides.
sure.
But I will come back to the Gaussian orbitals.
Yeah.
But the thing is that if you have an orbital like that, what you want to include in your basis set is another orbital which is the same thing, but a bit larger, and then another one which is a bit smaller.
Yeah.
Not higher energy ones, which you would do.
But these are not orthogonal.
No, they are not.
Yeah.
And actually, the fact that they are not orthogonal is an issue at some point when you put too many of them. All your matrices become singular or quasi-singular.
Because that's why then the hydrogen. Okay, but then if you have two hydrogens, then they would not be orthogonal either. So yeah.
No, but you can still do that, and that it's extremely bad. You start from typically if you keep the same number of basis set, you will get an error like factor 1,000 times bigger than. So this has been optimized to the core.
Mm-hmm.
Another one, simple diffusion equation. Simple diffusion equation. And that's a good opportunity for me to introduce the quantum Fourier transform. Okay, so I need to go back to the blackboard. It's 11:30. Okay, let me do the quantum Fourier transform and then we have the break. So Fourier transform, Tn m, is just exponential minus I 2 pi n m over 2 to the n, right? That's the definition of the discrete Fourier transform between so Fn and F tilde. And if you put a plus sign, you have the inverse, and it's you know that, right? Now, if you write n and m in quantics, well, you have an MPO for that, right? Let me call them X and K. Help to so let's say we have a X1, X2, Xn. And this is one case where the ordering actually matters a lot. I'm going to put here Kn. Kn minus 1 and K1. Why so? Because the rank of this guy is actually pretty small, typically rank 10 or so, that close to machine precision. It's approximately rank 10, not exactly rank 10. But if I put the other ordering for the case, I put K1 in front of X1, then I got maximum rank. So there is no compression. But if you put it in this order, take this function, give it to TCI, you will get a rank 10 matrix. And this is actually the quantum Fourier transform. If you have seen some Shor algorithm, for instance, or quantum phase estimation. So all this, all the class of algorithm of quantum computing that actually are supposed to give you a deterministic result at the end. They use quantum Fourier transform. And quantum Fourier transform is nothing but the Fourier transform in quantics. And good news, Fourier transform in quantics is a lower rank MPO. Therefore, we get it for free. So remember that if you do that with FFT, so there is a nice algorithm. So if you do that stupidly, computing time is 2 to the n squared because it's a matrix which is 2 to the n times 2 to the n, and you're doing matrix vector multiplication. Fortunately, some people some time ago found the FFT, fast Fourier transform algorithm. So you look it up if you don't know it, but you have a way to do that in 2n log to the power n. Looking at this, the fact that these are exponential, you can group things on FFT. This would be the discrete Fourier transform. This is the fast Fourier transform. FFT is probably one of the most used algorithms on the planet. I mean, half of the planet doing numerics is doing FFT, FFT inverse, and so on. And now the quantics, quantum Fourier transform. Well, suddenly it's n. So it's much faster, right? And so if you, of course, it supposes that you can put your function in MPS initially. It also means that in the Shor algorithm, we can easily simulate the end of the algorithm. So all the difficulty is actually in the beginning, where you do this modular exponentiation. If you have seen the Shor algorithm, I'm not going to explain Shor today. Okay. So now we want to solve diffusion equation. We want to solve diffusion equation. So dt of u equal dxx of u. If I Fourier transform that with respect to x, I got dt u equal minus k square u. I mean, and this is an ordinary differential equation for each value of k, which I can solve trivially. The answer is exponential minus k square t times u in k space, so u of k at t equals 0. U of k at t. That's it, you have your algorithm. You take your initial condition, you apply, you put it into TCI, you get its MPS. Then you do MPU, MPS multiplication with FFT to get u of k at t equals 0. This kernel, just give it to TCI at a given time. So as a function, so it's MPS versus k. And then you just do element-wise multiplication. We saw how to do that. It's the same thing as MPU, MPS. And now you get the solution at any time you want. You apply the Fourier transform inverse, and you get the solution. And you can do that with crazy initial conditions. So this is what we did in this. Can you switch back? In this, for example, so okay, this essentially just summarizes what I just said. You TCI everyone, take the initial condition, Fourier transform it, multiply by the kernel to get the solution, transverse it back. Okay, in this case, we put, I think, 40-bit, so 10 to the 12 points. And the initial condition was this thing, which was a bit ugly. So it's a square plus seeing something that, if you look at the zoom, that actually oscillate at two different frequencies. That could be commensurate, incommensurate, it doesn't matter. I mean, okay, it was just a toy example. And you get the solution at any time you want. You see it at infinite time, it should go to something uniform, because that's what the diffusion equation does. Uniformize things. But you can get like a super, you know, if you look at the zoom here, it's between 4.91 and 5.09. So you can really zoom, or we could zoom more, I mean, if we wanted to. And one solution is typically 1 second with 10 to the 12 points. So once again, it beats everything on the market. On diffusion equation is, I think, typically one case where this kind of approach will really shine. We have done it here using Fourier transform, but you can do it also with different. I mean, we see other examples later. So it's okay. It's already 1:40. Let's have a break for 10 minutes. Just 10 because I have a lot of things I'd like to say. And then yeah, we reconvene at 11:50.
The recording looks like, and I'm not really sure what the recording is, but we also need one. That's what
When I was I don't know. So I was told at the end. What did you hear about my guest going to be?
No, the speaker is the same.
Yeah.
Yeah, no, we might actually have to do that out of here. No, that's not. Yeah. It doesn't matter whether we actually yeah, but now I should be up and start. So after this, the problem is that if I now stop it, say it takes 40 minutes. Yeah. But I mean, you are not allowed to record me. They are just saying things. Yeah. Yeah. So we just need to take out the yeah, I probably right. That this microphone goes directly to it doesn't go beyond. That's because the microphone is connected to the main PC. It's not connected to the room. So and then there's no computer here that would get the audio from the.
But we might play the video file on this one computer. So when I tested it, for example, some recording,
Yeah,
I heard from the so I played something.
you heard sound that was going in the microphone. Which is the same micro, which is the microphone of the local I mean, this wireless microphone is the microphone. So this. Yeah, but now it will be next because they will be.
Okay, so this is a computer which is like this. And
Yes, you see so many people, if you look at they will, yeah, but they will probably complain.
Yeah.
and
Let's see, but you might, okay, you might want to have a question.
Yeah,
About
I think it's somebody's obviously.
Yeah.
So yes,
yeah, okay, we're
Yeah, but yeah, so this is this getting started always represent it and then actually it cannot be different.
Yeah.
So, I mean, they come to my computer, so I have to see more like. Yeah, I will take lots of time. Yeah. Thanks. Yeah, I mean,
okay.
that's kind of the one thing with the part. That's what the topic has called.
Okay, so I think that your name started growing with 3 and all the way to 7. What is the game? I don't suppose that's GDP. So it's a
Anything with the microphone button.
Yeah, but that's not anywhere now. It's still, yeah, and you can do that, but apparently the new. Still tough. Yeah, but what I'm saying is that it's a book. That's not this whole guy. More than this. Yeah, I just want to say. I mean, when you said pull up, on using a web page. No, yeah. I got to do it. But yeah, the idea so.
They're, I mean, they've made money. They are.
I used to go to the on computer, right? Like these, because whether you diagnose. I'm not even. I'm not really working, but what I did in my also about well, you guys spoke about this. Yeah, of course. Yes, I know that CSO will be so yeah, the business. Well, I guess a lot of people pays the pays the house. Yeah, so but Well, I guess I could get that. Ah, this is yeah. Well, so I get these concerned about the I already get five. How am I already still empty? So maybe you're those drivers.
We might do. We have a solver for we have a library.
Not out of the border, not like the right definition.
Yeah,
But
it's kind of a different question. But
it's in agreement with visual graphics structure. So I'm pretty sure what people don't think, but it's typically it's always for a student that knows what it takes 3 months to student to learn.
I guess probably would be less than 6 months.
Okay,
but he also pointed out that like we prefer to use ready-made library which varies certain tricks that allow that.
So right now, so we are actually designing but right now, if we really want to go status down, and the best combination, so you said that's a guy the best combination right now will be to use our library for CCI, there's a Julia version, combined with iTensor, which is an NCO library for from because they have everything but PCI, so everything is compatible. So we could get the first essays and all that. Anyways, our project, but just to put the thing together, is actually on the other hand, it's Julia, also it's some choice. The connection of the library that we also have the choice to know then how I use a point, but you can still use it. So this stuff is working full time, right? Both certainly special for the quality part, all very nice use, with volume of functionality. Yeah. Also, we are fast on robust. It's not really. You have when you are chunks of the player and you can grow this and we move from the drawing, but I lose this guy. I can try doing some this, I separate okay, like I went around when you are first figure out, and then you say, okay, you're in the viewers and then yes, I want to solve the lexically. And when you have the quantics layer, it's like, I want to take the area too. So really adding these functions that are I think the best one is also just either of quantitation of the tensor should behave as the tensor. You don't have that's the idea of the tensor is not all the tensor. It requires a lot of care to build abstraction in this complex term, so that everything behaves as if it were. Yeah. Okay.
Yeah.
Can we switch back to the? All right. Let's continue for we have 1 hour more. This is an example not from me, from the group of Jyväskylä, doing computational fluid dynamics, so Navier-Stokes equation. Navier-Stokes equation looks like a good candidate for quantics, because you know when you have you have this turbulent flows here. So here it's actually DNS is the benchmark, and this is a quantics solution. So in this case, actually match. On this turbulence, if you have done a little bit of computational fluid dynamics in your use, I mean, you're already in your use. Still, you have this Kolmogorov cascade. Right? So you have a cascade of things happening at different scale, which are a bit auto-similar. That's so essentially, since we are treating scales with different bits, it sounds like a good target to do Navier-Stokes, and indeed it worked very well for this case. And this is a time to discuss the question of Tero. What's the catch, right? And so first answer is we don't really know yet, because all these papers are let's say 2-3 years old. So we don't know exactly what's going on everywhere. Right now, we are really focusing on what works rather than what are limitations. But I would say the catch at the moment lies in the boundary conditions. So for instance, if you want to do turbulence, one of the problems you will be interested in will be, for instance, to have to solve the equations of a flow excluding the wind of the plane. Again, that's one big application of this kind of equations, is to see what is the perfect shape of of this wing. You don't want to create turbulence actually, because when you do, it actually creates friction, and actually costs you more gas. So you want the maximum. I mean, okay, you want to optimize this. And right now, if you try to TCI the function, which is delta of x minus r. So let's say, well, if you have a function which is 1 here and 0 there, so you want to really create a mask to solve your problem. It has a very high rank. I mean, unless this thing has a, if you are playing Minecraft, if this is your wing, yes, it does have a low rank, but this one doesn't. Right? Minecraft wing actually can be okay for certain equations. For instance, Poisson equations, so all the elliptic equations, they don't care about the precise shape. You can actually, you can make it a bit better by adding a bit more, and it will work.
The corner timing.
It's not necessarily the corner. Some shapes are difficult, some are easy. Rectangle is easy. Circle is difficult. It does not mean that it's because of the. So it's not really.
It's
really not. It's not yet well understood what. But the point I was trying to make is that if you're solving electrostatic problem for elliptic equation, the details of the boundary don't matter, especially if you're a bit far away. So you can get away with a Minecraft kind of boundary condition, and it will be perfect. So for Poisson equation, we are really going ahead, and we are pretty happy with what we have. For this, on the other hand, or if you are doing magnetism, for instance, you're studying the Landowicz-Gilbert equation for dynamics of a magnet, something like that, then the boundary matter. Also, we need to find a way through this problem. Also, there are a bunch of groups that are studying this, trying to find solution. Probably the solution will be something of a first mapping this by just distorting this, but not doing just a regular grid that we discussed, but actually distorting this grid to match a boundary or something of the sort. So there are several proposals, toy demonstration so far. We'll see where it goes. So that's one of the limitations that I see right now. Probably the biggest. With the rest, so far, we have been able to find solutions.
Is there a hope to do it in 3D? Like for an airplane, not just a cross category?
Yes, I would say yes, in 3D it will work. So for instance, one application I have in mind are the tanks used for pharmaceutical companies that are like, they want to mix this bacteria and with the food for the bacteria and stuff like that. And then it's really good to have Faraday boundary condition. You are happy with that. On that, I'm pretty sure can work in 3D. The plane, right now it barely works in 2D. It's maybe slightly better than but in 3D it's not as good as the best finite element vector. Go back to. This is another example of different applications. So it's a Boltzmann equation. So if you recognize the Boltzmann equation on the left, under an electric field, and the electric field is a gradient of a potential, and the potential satisfies a Poisson equation with a density of electron, which is the integration of this. So Fs is the probability to be at position r with velocity v. If you integrate over v, you will get the density of charges at position r. So this is the kind of equation you write for typically a plasma, so like classical plasma. Yeah, so if you just shoot a high intensity laser on a bunch of things, you will get something described by that. So typically, people is interested in nuclear matter for fusion or this kind of things. We study this kind of problems. And you see again, like on the left, you have the exact thing. On the middle, you have the exact
with some level of compression on the right. So D here, this big D is a bond dimension. Bond dimension is either written as chi or big D. Two screws fighting very hard. And you see, this is a case also where you have a good level of compression. I think this is a good case, the case that will work very well, because Boltzmann equation is essentially some sort of diffusion equation with a drift term. So we make a mixture between a layer on drift, on diffusion. Poisson is an elliptic one. So everything is good here. It should work very well. That's a case where I think it will generalize. This is Poisson in our own group. So you see, you can actually, this is 1 kilo, so 1,000 pixels, 1 million pixels, a billion pixels on the 10 to the 12 pixels. And you have the solution. In this case, it's a benchmark, but we have the same calculation where we don't have the exact solution. And you have zooms on the second row. And then you have zooms of zooms on the last row. You see, if you zoom too much, if you don't have enough pixels, you get something bad. But eventually, you can reach a precision you want. There was an additional thing that we had to do to make this work really well, which is linked to what people do in multi-grid method. So if you take the best state-of-the-art method for solving partial differential equations, they are called multi-grid. So essentially, they mesh the system with different meshes. So there is a very coarse mesh, then there is a better mesh, and then a fine mesh, and then a very dense mesh. And then you want to solve your equation using an iterative scheme. You always want to use an iterative scheme because if you don't, then things take forever. So typically Kirchhoff methods. But Kirchhoff method, you update your solution by taking your vector and multiply it by your matrix. But if the matrix is local, then it can only, when you do one multiplication, it only explores things locally. So if you have a very, very fine mesh, you need to do a lot of multiplication to actually start to explore the entires. So this multi-grid, they essentially work on the large mesh. Then you make big steps when you do Kirchhoff. Then you interpolate to get something which is a starting point for the middle mesh. You iterate again. You actually make this better. And then you go to the fine mesh, iterate. And then from that, you can go back up. And so you get better approximations for the thing. And you go up and down. And eventually you converge to the solution. So these are things that are, if you just use a state-of-the-art finite element solver, it's essentially doing that. But at least it's one of the leading methods. With quantics, you can do that out of the box, right? So essentially, you can start your solution with a certain number of bits, and then add one more bit. You double the number of points. You can interpolate. We have an NPO for interpolation. And then you can increase the number of bits. You can go up and down, but it's totally natural in this fund. Also, in that sense, we didn't use a straight out of the box NPO LPS equal LPS solver. That didn't work very well. I mean, it worked up to a certain point. But with this additional trick, we could make it work to arbitrary number of bits. So you have to adapt at some point your algorithms, improve them to a particular case that you are looking at, because there is additional structure, but maybe you can take advantage of this structure to have better solve. That's a Finnish example. So from Marcel, so it's a group of Roselado. So with ourselves also. So it's Gross-Pitayevsky. So it's so now you want to evolve things in time. You have a Laplacian, you have a potential. In this case, the potential is very weird because it's actually incommensurate potential. So it's a bunch of cosine that are not commensurate. So it's like a quasi-crystal. And then Gross-Pitayevsky means that the equation is nonlinear. You add this nonlinear term here in the equation. Okay, there are multiple ways you could actually solve these things. The way we chose is to actually split the Laplacian on one side on the things which is diagonal in space on the other side, so V on the side square. You trotterize. And then you use the fact that the fast Fourier transform is free. So you essentially add your initial state, which you
put it into MPS form using TCI. Then you apply the kinetic energy, so exponential minus I k square t. So first you Fourier transform to k space, apply the kinetic energy with a small t. Fourier transform back to real space, apply exponential minus I vt. Then you need to apply exponential minus I psi square t applied to psi. This to use PCI to put exponential minus I psi square t into MPS form. And then you Fourier transform to k space and you continue with kinetic energy, and so on and so on. And you see in this case, so you have again the solution. So it's a wave packet, a Gaussian wave packet with some velocity that you follow in time. But this is a snapshot at a given time. And if you actually zoom here, you get this thing. I think it's beautiful. This is why I'm showing you, because there is some poetry in that plot. And you can actually zoom on here. It's a bit blurred, but that's actually the screen, not the solution. We have I think 1 million points per dimension in this image. So that's a case where it worked very well. Okay. Yes. Let me. Yeah, maybe we can switch. Let me introduce a new problem. And it's time to zoom out and start to look at the big picture. Particular quantum computers. If you look at what quantum computers are being proposed to be good at, and I have a good slide for that. I forgot to put it there, but the slide I have, which I usually start from, is from the French government when they started the French quantum flagship project, and they said quantum computers are going to change everything. And then there was actually a 12 pages document. Then they say, okay, they are going to change the way to solve problems in energy, to solve problems for health, for the way we actually feed ourselves, security. There was a list of several problems. And actually, if you knew the science behind it, behind each of them, there was actually at least one scientific paper. And actually, if you look more carefully, you realize that all these papers were essentially about the same thing, which is solving chemistry, solving the chemistry problem. So I'm going to introduce a problem that everybody is interested in, and that has been proposed for quantum computer. And then probably at the end, depending on the time I had, I will tell you what people have in mind for the quantum computer to do that with the quantum computer, and put in contrast what we can do with classical methods. Okay, so this problem is well, it's you suppose that so you have a molecule. You suppose that the nuclei are fixed. You forget about the quantum fluctuation of those, which is fine down to 0.1 milliards, let's say. It's actually a good approximation. So what you want to solve is, so your method is minus h bar over 2l, integral over 3d, pi dagger r, translation psi of r, you put the spin also. Minus integral dr e square over 4 pi epsilon r minus r I sum over I sum over speed psi dagger psi r sigma. So this is actually the input of the problem, the position of the nuclei, with its charge, Z. And then what makes this problem difficult is that you have to also to take into account Coulomb repulsion. And that's because what makes it interacting on the. So the input of the problem are the position of the nuclei. And if you can find the ground state of this versus position, then you can solve a lot of interesting problems. For instance, you can, so if you want to see whether there is for a chemical reaction, for instance, you will study the energy as a function of, I don't know, for instance, you have, I don't know, this H2 plus O2, and then you at some point there is some complicated thing here, and at the end you get a H2O plus whatever O along some directions where if you can get this energy here, you get the activation energy, and essentially Arrhenius law tells you what is the rate of having this reaction. So whether this is big or small compared to KT will tell you whether the chemical reaction takes place or not, and you need to explore different paths. And there are also tons of algorithms to do that, but really what you need to be able to calculate is the energy of the ground state versus position of your N nuclei. No, the microphone is on. Right. Yeah.
Yep. Sorry. Okay, let's call that the chemistry problem. Of course, you can add more complexity to that, but it's already. And the first thing that you do when you want to solve the chemistry problem is that you can't work in the full space. You're going to select a basis set. Okay. So you're going to introduce. Oh, by the way, I just introduced. Everyone is familiar with field operators. Yes.
I
mean, I don't have time to do a full course on this anyway. So if you don't, just take that as a kinetic energy, attraction by the nuclei, and Coulomb repulsion. So the first thing you do is you define orbitals. So you have an orbital alpha. So this is actually a field operator. It's a destruction operator in orbital alpha. And so you need to define, to give yourself some orbitals. Ideally, you could a full basis set of of L2, but in practice, you just take a few because this is the only thing you can afford. And you want to rewrite this Hamiltonian in this basis set. Okay, so you can do it, and you get H. It's not exactly H; it's an approximation of H truncated to this basis set. So we have alpha equal 1 to m. So we keep m orbitals. And on the Hamiltonian, will look like H alpha beta, C dagger alpha C beta, plus V alpha beta gamma delta, C dagger alpha C dagger beta C gamma C delta. With V alpha beta gamma delta, I'm just writing this one. Imagine what H alpha is. It's integral dr in 3D, integral dr prime. Then you have the product of 4 of these orbitals. Position R, position R prime. Half of them are complex conjugated and divided by R minus R prime. E square over 4 pi epsilon naught. So we call them Coulomb integral. So you just do the change of variable You replace each of these psi by some stuff like that, and you need to do the integral over space. You get this. There is, of course, here summation over alpha and beta, and here summation over alpha, beta, gamma, delta. I'm being sketchy here. I mean, well, this is essentially correct, but if you want to do the actual calculation, it would take more time than I have. So 6D integrals. 6D integrals are tough, right? If you, once again, 1D, 2D, 3D, Monte Carlo, before TC. So because of that, for the last 30 years, the chemists have been working with phi alpha of R, essentially was a sum of something called zeta equal 1 to 2, maybe 3, maybe 4, maybe 5 at most. Gaussians. Right? So that will be for the s orbitals. And then you can add a polynomial in front that corresponds to the orbital part of the p or d orbitals. But essentially, you have a Gaussian. Right? And why did they? So this is what people call Gaussian basis set. And why did they work with Gaussians? Well, because that's all they could do. I mean, that's really it. With Gaussians, we actually do have quasi-analytical formula to calculate this. People have been used Gaussians on design Gaussian basis set for each atom in the best way they could by putting a bit of this. So they know that at the end, the important one will be more or less this distance, this zeta. And then maybe they will add one a bit bigger, one a bit smaller, maybe two if you can really. But at the end of the day, so if you see, you will see things like that, like CC, PV, DZ. That's a typical name for an orbital, basis set. And D here means double. But some of the orbitals add the valence of the have two Gaussians. Then you will see also triple zeta, quadruple zeta, and 5 zeta. So same thing like CC, PV, Z. So this is, when you see this for the first time, I mean, I literally had to make myself a glossary of all the acronyms they are using. So typically, this, for instance, this is one of the best basis set. Double zeta is actually not really acceptable. If you look at the precision it gives you, it's actually very bad. Triple zeta start to be correct, more or less, but not to chemical accuracy. If you really want to do chemical accuracy, you need to do this, and that, and extrapolate. But you can never do that because when you can do triple zeta, it's already usually the limit of what your computer allows you to do. It means that it's very rare to actually get the you can get chemical accuracy on H2, on H2O, small molecules. But on the molecules you are actually interested in, usually you don't. And so that's something also, when you look at a claim by a quantum computer, they always, oh, we have reached chemical accuracy. What they really mean is that they have reached chemical precision, which means that for the basis set that they are using, the result has a correct precision. But what they are not telling you is that this basis set is far too small to be actually useful in practice. And there is one that you will only see in quantum computer papers. It's called STO, like STO 3G or STO 6G. And if you look at a quantum computer paper, most probably, with probability close to 1, it's using this, which is much worse than double zeta. and actually it only gives you, so I have examples. For instance, you must have seen this curve, energy of the hydrogen molecule versus the distance between the two hydrogen. Get some curve which is like that. And you see the exact curve, and then you see what you can get with a quantum computer. Yeah, it's actually not too bad. So first, when you see a curve like that, on this curve, last time I was at a March meeting like 2 years ago, I saw this curve like 8 times. Why? So first, because it's STO, so you can get it. Which means in this case it means 2 qubits, one s orbital per hydrogen. So it means that it's essentially diagonalizing a 4x4 matrix, which you can do on a quantum computer, but you may also do with different ways. The results are not that great actually when you look at the scale here, because this scale is typically in R3s. If you have a scale that goes up to 10 R3s, you are talking about something, depending on the paper, something between surface temperature of the sun and core temperature of the sun. Anywhere in between, right? So what we want is 300K accuracy, right? So something that looks small actually might be actually very big for a computational chemist. And also, as soon as you start to look at this basis set, well, you get something that actually looks like that. And this can be typically like 5,000 Kelvin, for instance. Always make sure that you differentiate chemical accuracy with chemical precision. So one project that we started in my group, to go back to quantics, is okay, 6D integrals. I'm not scared of 6D integrals with quantics. So actually now we are trying to replace those Gaussian orbitals with quantics orbitals. You have infinitely more flexibility. You can actually calculate these orbitals instead of defining them with only 2 parameters and just doing your best. So we have algorithm now to actually get gradient descent of the energy with respect to the orbital itself and stuff like that. Why is it so important? Is that if you just take just one s of the hydrogen atom, let me remind you what 1s is. If you look at your quantum mechanics 101, when you did the hydrogen atoms, it's expansion as r divided by the Bohr radius. And so with Gaussians, you are trying to express this as a sum of, let's say 3 for triple zeta Gaussians. So you have something with a cusp at the position of the nuclei, and the cusp is important. It's really why the energy is not diverging. So you need this cusp to actually in your solution. And you are trying to approximate that with one Gaussian plus another Gaussian plus maybe a third Gaussian. But you will never get the cusp, and you will never get the tail neither. So actually, we know that these Gaussians are not very good. But I mean, people use them because this is the technology that was available. So there is a good, okay, we are spending some energy in the group to try to go beyond this. What?
So the box space, I mean, you this, but then you have the.
I'm talking here. So for the moment, I'm just talking about the orbitals.
Yeah.
I will go back to the many body problem a bit later. So this is a partial differential part of the. We're actually solving functions. There are no many body. Of course, you need that for the many body. So you see here, it was just checking that we could actually calculate these orbitals. Okay, you get in this case it's for lithium hydrogen. Actually using Gaussians because we needed something to compare to show that it was Now we can actually redo these things for other orbitals that are not Gaussian, but here we just compared with an analytical solution of the Gaussians, and the fact that everything is blue on this line means that actually we could actually calculate these things with the precision we want. Okay, so now it's time to go back to the many-body problem, and I have half an hour. Okay. I'm going to skip most of the slides here, just mentioning this. So now you want to go back on the many-body problem. And we have all these tools that we have been discussing for a week. So some of the things that we have been doing in the lab was to use a tool to go back to the many-body problem, but not from the traditional perspective where we have an MPS for the ground state. Rather, we will use quantum field theory techniques, in this case, Feynman diagrams, and use TCI and other things to calculate these diagrams. Okay. And it would actually take a week to explain all the details of how you get there. Just flashing quickly some. In this case, we were looking at the Anderson model, so it's essentially a quantum dot connected to leads. Which is what leads to quantum physics. I would say it's a modern way to look at quantum physics because the impurity is artificial. You make it, you control it, you can design how much it actually coupled to the bass. So I briefly discussed quantum physics earlier in the week. Experimentally now, you can really study this thing with a lot of control in direction free within quantum electronics. And this is so there is a bunch of sites which are non-interacting, and the interaction is on a single site, which is here, about like interaction on single site. And I don't want to spend too much time on this. For those of you that, I don't know if you have seen this curve, diamonds, the Coulomb diamonds. So there is a lot of physics in these simple systems. You can actually, so you get the phenomenon of Coulomb blockade. And people are using that right now to essentially try to trap a single electron and then use it as a qubit to build a quantum computer. You see the loop is complete. We come back in circle. This is a particular experiment from a friend, actually on a transistor which you could find in your cell phone, but this experiment has been repeated thousands of times in different systems. Yeah, okay, I'm not going to explain that. So, or maybe if you go at low temperature, you will see. So this is the quantum physics. Quantum physics. So the blockade that you saw earlier, these diamonds, they are barely visible here, but you have this very nice strong line that is really correspond to the quantum physics. It's really the fact that you have this now single spin in the impurity that's going to be screened by the bass, and it creates a resonance at the Fermi level. And so this is actually what experimentalists observe. This is the conductance versus bias voltage on the gate voltage. The gate voltage is moving the position of the impurity, and the bias voltage is really you are injecting that much current in your system. And so the tough nut is to find this guy. So what Wilson did, the NRG, could essentially solve this thing at equilibrium. But we were very, very frustrated by the fact that this map has been measured also maybe not thousands of times as Coulomb blockade, but at least hundreds of times. We could not calculate this thing in a control way. And so we have designed all these things with this Feynman diagram calculation. Now we have it here, you see. So this is so we can actually solve this thing exactly up to certain precision, but we know the precision. So that was for us one of the big success of TCI, to actually do the integrals of Feynman diagrams. Yes, it's each pixel is 100 million integrals in typically 20-25 dimensions. Just to show you that it actually works for real problems. We don't have that many real problems so far. We are mostly exploring about what we could do. But that was a tough nut. We have tried for years to not only my group, other groups. And now we can actually solve this.
There's some small parameter.
No. Yes, interaction. But small means 12. So it's not that small.
Yeah, the question is that so basically because it's small, not small, you have a lot of diagrams, I guess, but
So essentially you're doing an expansion. I will make a short answer. Let's say you calculate the current versus bias voltage, etc., but interaction, U. So what's the bare output of the code, when you sum all the Feynman diagram, you get the order 0 contribution, the order 1, order 2, and so on, up to certain maximum. You do everything by hand, you will calculate order 1, you will calculate order 2. If you're Russian or Japanese, you may go to order 4. If you're not Russian or Japanese, you just forget it. You just stop at 2. Right? Here we can do now 25. Maximum we did was 30, but 25 if you really want to scan parameters and stuff. Now, this IN is typically, it scales as 1 over factorial n. Probably. Which is essentially 1 over n to the power n. So, it means that IN u to the power n is essentially u over n to the power n. So you need big N to be bigger than u. And then immediately you see if u is 10 and big N is 12, this is 0.8, but 0.8 to the power 12. It goes very, very quickly to 0. So bottom line, if you want to go further in u, you need to get more orders. No, u is in the scale of of gamma being the connection, the lifetime of your resonance before you switch on interaction. So in practice, we went up to 12. And for some cases, using this cross extrapolation, for instance, we can go up to u equal infinity by extrapolating the result. Just to show you this, so here Qn is the same as In, the kind of data that you get. T here is the time since you switch on the interaction. So actually what you do is you switch on the interaction and you wait until it relaxes. And the reason I'm showing this plot here is that you see that the same technique allows to calculate numbers that are varying from 10 to the minus 95 to order 1. Typically at the end it's 1. Typically the order of the low order 1. I'm not aware of many techniques where you can get such large scale of things. I think very special to this. Experimental level for sure. This plot also is interesting. I'm not going to give you all the details, but it's one case where we actually learned TCI was actually when all the pivots were kept inside a small box. So let's say between 0 and 1. And then we extrapolated the result to 0, 10. You had to go there to get the exact result. And it's interesting to see that so this is essentially the size of the small box. And you see that as far as size from between 0 and 2, so you have seen essentially a very, very tiny volume, between 0 to 2, so that's 2 to the power, this is order 10, I think, so 2 to the power 10. But the real volume you need is 10 to the power 10. So the ratio between the two is 5 to the power 10. It's a huge number. So you have seen a tiny, tiny corner of the configuration space. Nevertheless, you get 5 digits to the final result. That's really the strength of being low rank. You can really extrapolate. It's not only about interpolation. You can really extrapolate outside of what you have seen. If, of course, the object you are looking at is actually low rank. Also, this is a case where actually the entanglement is very high. If we have used basic DMRG for an MPS, the way I taught you, it wouldn't work. But it's working here because we are actually looking at the entanglement of Feynman diagrams. It has nothing to do with the real quantum entanglement. So it's taking another route, different mathematical object, entanglement, totally different meaning. So it's not because it didn't work with one route that it will not work with another route. The entanglement is not something physical. I mean, it is when your MPS is the ground state of a given Hamiltonian, then it has a meaning in terms of quantum entanglement. But if you're taking another mathematical route, then this meaning is gone. And it has a different meaning. Might or might not be physical. Probably the last one. Yes. Last one, and then I can. The only thing I want to show here is this plot here. This is a sign problem, again, for this Feynman diagram, versus epsilon d. Epsilon d is essentially the plunger gate, if it was a quantum gate. It's one of the parameters that controls the thing. And the sign here goes from something close to 1. Close to 1, you can do Monte Carlo, to something close to 10 to the minus 5. And when you sign average sign of the stuff that you are trying to integrate is 10 to the minus 5, it means that you have an increase of computing time by 10 to the 5 squared, so 10 to the 10. So if you want to use quantum Monte Carlo to do this integral, if let's say you can do this one in 1 second, then this one you need 10 to the 10 seconds. On the bottom line is the error that actually you see using TCI for the same computing time, and it's completely flat. So it's one case where Monte Carlo fails completely. We had big sign problem, we could not compute. In this case, to the fact that we really want to have quantum transport, so we are working with real time, so a lot of oscillatory things everywhere. So huge sign problem, nothing works with Monte Carlo, but TCI is based on totally different structure, and then it works. And that's it for the slides. I have 20 minutes left. I'd like to discuss one more thing about quantum computers on classical approaches. Let's see. That's a part that I had included in the first. So I had written some notes, and then I just removed them because I thought it was too much. But apparently, I have some time to at least hint about it. So we discussed quantum computing, but I have not given you any quantum algorithm. Well, because I had to make some choices. I'm going to give you one now, which is called VQE, a variational quantum eigensolver. That's the algorithm that most people are focusing on where most of the hope for solving chemistry is. Okay, so the idea is to solve the quantum chemistry problem with VQE. And in front of VQE, I'm not going to give you, in front of VQE, if you want to solve chemistry, you could put DMRG. You could also put chemists have special techniques. One of them is called couple cluster. I'm not going to discuss this one. So DMRG is currently one of the best solver. Couple cluster is also quite good, but in different applications. So essentially, if you take an organic molecule, like, I don't know, like methane or something with only carbons, hydrogen, or oxygens, then the mean field approximation of the many-body problem is actually not so bad. So R3-Fock, another one, is not so bad. And if R3-Fock is not so bad, then couple cluster will actually work very well. So couple clusters, these CCSD methods, chemists usually consider that they are like the best kind of things they can do. They will work very well for something like, I don't know, let's take a nice molecule. This is a nice molecule. Very expensive in Finland, but a very nice molecule. On the other hand, as soon as you have a shell which is not fully full, then CCSD, R3-fork is not a good starting point anymore, and then these couple cluster techniques, they collapse. One of these things that you may have heard of is the so-called FEMOCO. FEMOCO, if you have followed a bit quantum computing literature, so FEMOCO is iron molybdenum cofactor, and essentially it's something that contains I don't know, I think 6 irons and maybe 1 molybdenum. And it's a core of an enzyme. And this enzyme is taking the nitrogen of the air, N2. I'm using really my table in very, very bad way. Okay, sorry. It's taking N2 and transforming into NH3, ammoniac, which is what you want for fertilizer. Okay? So when you read, for instance, quantum computers is going to make us to solve food, world hunger. What it really means is nature actually has a way to actually make fertilizers. I mean, to break N2 and make it turn into something organic. Otherwise, there would be no life on Earth. I mean, the same way nature can actually break carbon dioxide to actually, it can also do the same with N2 using this particular enzyme that has as its core an iron cofactor. It works, and it works at room temperature because this is where plants actually work. If you want to do that in a plant, you need to use super high voltage to actually crack N2, and using some German name that I never remember, maybe Christoph does. Do you remember the name of the, when we crack N2 using like these super high voltages plants? It's a German name. This one. It is actually using a fraction of the electricity that we use on the planet, like 3% or 1%. Yeah. No, but it's actually, you do crack the molecule. You need actually to put large voltage. Not super high, but you need to tens of volts or hundreds of volts. I don't know. I can't remember. We can look it up. Anyway. It's using tons of electricity. And so someone came up with the idea like, look, if we can study FEMOCO with a quantum computer, then we can maybe optimize it, make it better. And then we can actually do that at room temperature. And then we will have solved world hunger. We'll have solved the energy crisis problem because we stop using 1% or 3% of electricity to do that because it will be done. So when you see this kind of claim, usually there is one very simple idea behind FEMOCO in this case. And by the way, so if you look at so there are papers looking at what it would take to solve FEMOCO, and then you look at, for instance, the basis set that they are using, and too bad, it's so small that really we would have like still an error of like probably sun temperature, surface sun temperature kind of errors because they just took a basis set which is too small. It happens that I'm now discussing with a lot of chemists for this project of using tensorized orbitals, like these quantics orbitals. So I'm discussing with chemists, and one of them is actually the world specialist of FEMOCO. And he was also super pissed because all these resource estimates that have been done for quantum computers, they used only the iron and the molybdenum, but they didn't take the sulfite that were around. And it's well known that if you don't include the sulfite, you immediately get results that are completely wrong. So they didn't. So essentially, this problem starts at a number of orbitals, which is probably in the many hundreds or few thousand. And the resource estimated had been for 53, 50 qubits, essentially, 50 logical qubits, which become a billion qubits when you take quantum error correction into account, and you get one number every day, But of course, if you scale that to 1,000 qubits, since everything scales to the power, I don't know, 5 or 6, or then it means that you will need years to get a single number. So, okay, that was that. I will just stop these general comments. Let's look at VQE in the remaining time, which is now close to 0. No, still have 15 minutes. And in front of VQE, I will put VMC. So VMC is what we do. I would say it's the closest thing to VQE, but on a classical computer. So VMC stands for Virtual Monte Carlo, and it's a technique that are now has a lot. I mean, yeah, you will see there is a lot of connection with tensor network, and it's a very interesting idea. So what do you do in VQE? You start with your qubit. You put some gates. On these gates, they are parameterized by some angles. So you have a circuit. On this circuit is actually, so it's parameterized by some parameters. I don't know, like a certain number. And you say, this is my variational ansatz for the ground state of my molecule. And then you need to do several things. First, you need to calculate the average of the energy. Okay. And here, essentially, you have all these terms. You have n to the 4 terms. And okay, each of them, essentially, not each of them, but almost each of them is a separate calculation. So maybe you need to take qubit 2 on the x, measure it along the x basis, and qubit 3 along the y basis, and qubit 4 along the z basis. And at the end of the day, you have a bunch of terms, so you need to typically, here, these are m to the 4, so you typically need m to the 4th term. On all of them are of order 1. So actually, the variance of these things is typically 1. And the typical error that you will get is sigma over square root of the number of repetition. So let's call that n repeat. Okay. Now, VMC, what do you do in VMC? Exactly the same thing. You have a function psi r, where r is typically, for instance, the occupation of the first orbital and the occupation of the occupation of all the orbitals. And you give yourself a function parameterized by parameters theta, the same way you do with for VQE. So when I was young, we used to spend a year designing the best function that would be exact in this limit, exact in that limit, try to interpolate nicely. Now we don't do that anymore. Now you just take, so N1, N2, Nm, and you create a big neural network. Create a big neural network. What is a neural network? It's nothing. I'm not going to introduce the details because only 10 minutes left, I think. Yes. But a neural network is really it's really an ansatz that you give yourself with tons of parameters, the reckoning weight, and then what you do is at the end is you have your ansatz theta, optimize this with respect to data, for instance. So this ansatz may be a transformer if you want to have a large language model, or it may be autoregressive model or not. It may be so there are okay. CNN for images. Okay, there are a bunch of them. But at the end of the day, it's just like you put some layer, you add to give that to nonlinear functions that are the neurons, and continue like that. And then you need to calculate the energy. So the energy here is essentially you have the Hamiltonian. Oops. So you want to calculate this average. And the only good thing about your Hamiltonian is that for a given R, which is R span exponentially, it's an exponentially long possibilities. But for a given R, there are only a few, typically n to the 4 non-zero R prime. So you rewrite that, okay? You rewrite that as psi square times E of R, where E of R is 1 over psi R, sub over R prime, H of R prime, psi of R prime. This you can actually compute. It's the sum for given R is actually pretty small. Okay, and this is the average of this guy with respect with this probability. And this you do with Monte Carlo sampling. So you typically run Metropolis algorithm, for instance, or if it is an autoregressive neural network, you can actually directly sample this guy. If you have never seen the Metropolis algorithm, Google it. It's one of the also, it belongs to the list of amazing algorithms. And you will get the average of the energy for more or less the same cost, but there is a huge advantage. Is that if you find the ground state or something close to the ground state, you see, if you find exactly the ground state, then ER, so this is actually H times psi, is equal to E psi. I divide by psi. So if I find the ground state, then ER is actually the energy, the ground state energy, and it doesn't vary with R. So when you are going to optimize your function, the closest you get to the ground state, the less ER will fluctuate. And so this gives you a huge advantage with respect to that. The fact that you can calculate the energy directly as a whole, as opposed to measure separately, means that you're here typically, so again, you want 4 digits. 4 digits means 10 to the 8 repetition. So you need to repeat your calculation. So you create your circuit 100 million times. That will give you 4 digits. Here it's typically 10 to the 3 what we do in actual calculation. So you just lost 5 digits with respect to a classical algorithm. But it's not finished. Now you need to do the gradient. Right? You need to calculate the gradient of the energy with respect to these parameters. And here, essentially, you need to calculate this one by one. So if I have n sharp parameters, this is n sharp calculation. Each of them you need to do with more or less the same precision. So it's n sharp times n repeat calculation. Here it's just n repeat. And this is it's called automatic differentiation. So for the price of evaluating a deep neural network, you actually get the derivative with respect to all the parameters for the same price. So you go once forward, the other backward. You may have heard about this as called backward propagation algorithm. Again, Google it. And it means that for the price of one call, you get the full gradient. You need the gradient if you want to descend. If you have a huge space, if you don't know if you don't have at least a compass, you're not going to find the minimum. And so typically, I don't know, n sharp, 10 to the 4. It's hard to imagine that you can get good on that with less than 10,000 parameters. Typically, now the good ones are more especially the more complex your molecule, the more parameters you will need. You just lost another factor 10 to the 4 with respect to VMC. And I can continue with that. What do I have on my list? Oh, okay. Well, thank you. So there is a question about whether the ansatz that I have, psi itself, is it a good ansatz or a bad ansatz, right? On there, I mean, I would say the question is still open on both sides. Initially, the people in the VQE community, they were considering what was known as a hardware efficient ansatz. So essentially, they were packing gates everywhere. And because you don't want to have something which more structure, because it means that you have some idle time. And idle time means more decoherence, right? And it turned out that this was actually not working very well. It was actually working very badly, and in a provable manner. So the mathematicians did some interesting work there. You may Google the name Barren plateau if you're interested in that. And it's due to the fact that if you take something random, essentially you get a random vector. And so you have on a random vector, it's also something you can prove is actually totally uninteresting vector. So you take a random vector, for example, the correlation function between different qubits, all these kind of things are trivial. No correlations, nothing. Which means that if you take a circuit which is too naive, it will be packed with random vectors. And the interesting ones will be only like very, very tiny line, like hidden in this zoo of shitty ansatz. And in practice, it doesn't work. You can't find your compass is not helping you, especially since your compass is actually noisy. You remember that you're calculating this gradient, but with a certain precision that depends on the repetition. And so people could not do anything really useful. They started to consider essentially the ansatz coming from chemistry. So essentially something like CCSD. I have no time to explain what CCSD is, but totally inspired of what people do in chemistry. But then, of course, then these needs much longer circuits, and then you can't actually do that on your quantum computer. So the only thing you have for these circuits are simulation on classical computers. And so I would say it's not clear. Here, on the neural network side, it's very, very open. All this is very recent. There are a few cases which are very promising, where people could actually get super nice result, but still it's in its infancy. This process of really trying to decrease the energy by looking at the gradient of the energy, you can get stuck in local minima. It's a bit messy, so it's not. I would say it's not yet a method that people really use. Chemists don't use it yet. It's really like mostly physicists developing this thing. And but on the other hand, it's a very good. Even if it doesn't really work at the end, it's extremely good comparison point with respect to quantum computers. And you have as much entanglement as you want in neural net. Again, neural network, think about it. So if you are wondering neural network versus tensor network, the answer is very simple. If tensor networks work, you just go for tensor networks. If it doesn't, then maybe neural network is a solution. But it's much less structured than a tensor network, and so it has its advantages. You can have much more. But of course, calculations are a bit more messy. You have to do Monte Carlo and these kind of things. And I'm reaching the end of I already reached the end of my time. So I will stop here. So we still have 2 hours this afternoon to try to see how far we can go with this simulation. I hope that you got something out of these lectures. It was fun for me, at least. So one person in this room is happy. I made you an offer at the beginning of the lecture. It's still on the table. So if some of you want to propose something to illustrate the lecture note, essentially I will be in Lapland for the next 2 weeks. So I won't touch it until early September. So if you want to send me something before early September, I would. If someone wants to. So the criteria is that essentially, if I think it adds something to the note, that it illustrates some point, it makes it more concrete, then I will put it in the paper. So, no, I will not put everything you send me to the paper. So if the code has to be reasonably okay, if it's not so good, then maybe Christophe will clean it. If it's really too bad, then I won't put it in the paper either. We will publish the code with the plot. Or not. I mean, okay, it's up to you. And that's it, really. I have no time for questions. Maybe I will take the questions at the beginning of. If you have general questions about the lectures or about today, I will take them at the beginning of the. Thank you. Good lunch.
Okay. It's